Hiya, folks. I guess we'll just get started here. It's now 5:30. Welcome to another Common Lisp Study Group. I'm your host, Ram Vedam from Atlanta Functional Programming. We'll be continuing our discussion from last week on Chapter 11 and 12 of Practical Common Lisp. Obviously, if you remember from last time, we stopped at our discussion of hash tables. To get things started here, let me first share my Emacs screen here. Just 1 second. Can everyone see that? Is the font all okay?
Looks good to me.
All right. Let me just maximize this window a little bit so I can actually see my notes here. All right. So.
And now you need to increase the font a bit.
All right. Control X. That looks like it's a bit too big, but okay, I'll go with that.
That's good.
Okay.
Yeah.
Let me just do the same thing on. All right. So hash tables are a built-in data structure inside Common Lisp. It's one of those things that are actually unknown. From when I first started with Lisp, as I went through this book, I didn't realize that hash tables were available. So it was kind of a pleasant surprise. And it's actually a fairly well flexible data structure. To get things started, to make one, you could just simply call make hash table with no arguments, as you can see here in this example that I just I'm hiding this guy. Hold on, apologize. So if we go in and just compile this dude, we'll see that we can end up creating a make hash table. So what does that do? Make hash table, if we actually look at the signature, takes in by default some sort of test function, and there are some key value pairs that have some defaults in there, like minimal hash table size, whether or not you want to rehash what the threshold is. And you can even specify things like a specific hash function and so forth. But those are implementation details. By default, the test function and by test function, I really mean key membership to see if something exists inside the key store to actually retrieve a particular value that's stored in the hash table. The default function that's used is actually the EQL function. Now, we've talked about this in previous study groups, but just to remind you, Common Lisp has 4 standard equality comparison operators: EQ, EQL, equal, and equal P. And I think someone mentioned this. I don't remember who it was in the study group in the past, but someone mentioned that in order of flexibility, like the more letters there is in the function that you're calling, the more flexibility that function actually has. So like EQ only looks at conses, EQL checks to see if they're the same object, equal checks if they're using you can use it to actually do like string comparisons, and equal P is the most generic one of the 4. When you're creating hash tables, you can use any of these 4 equal functions. So like you see here, I created an example of a hash table called string hash table that if I go ahead now and try to set up a value here, which by the way, when you're trying to add values into the hash table, it's just a setup on a get hash, and I do test key on that string hash table, and I specify my name. You'll see that it actually succeeds, and it will insert that into the hash table. But if I try doing that on what I did earlier, which is test key on a hash table, which is using the default EQL function, and I try, adding my value into there, I'm gonna. I change that. Hold on. That
You just won't be able to get it out again.
Yes. Okay. It'll insert it, but you won't be able to actually retrieve it because it's going to try now, and I just simply try and retrieve that, it's going to complain. It didn't complain. Oh, it's because it's not it's treating that as an identification. And EQL, if you do EQL test key, they're not necessarily the same object. And that's because EQL doesn't, it's treating them as pointers. It's doing almost a pointer comparison to make sure that it's pointing to the same memory location. Now, if you look at, if I do a get hash on test key for string key hash table, which is using a string has a test comparison using the equal operator, you'll be able to get it. Now, you might have immediately noticed something here in the REPL, and that is, what are these two return values? It's obviously sending two return values. Well, hash tables in Common Lisp will return the value and whether or not it found the actual value or not. So you can check the second return value to see if you actually had an entry. And if you did, then obviously the first value will not be nil. One way of actually leveraging both of this is something called multiple value bind. Now, I'm going to be only touching briefly on this just because the chapter 11 doesn't really go through too much detail on what multiple value bind actually does and the entire notion that a function can return multiple values. But to make a long story short, Common Lisp does, and to introduce this concept, Common Lisp does support returning multiple values, and there's a specific way of doing it. For the time being, we're just going to leverage this multiple value bind function, which allows you to specify, let's just go through this here. The first two options here are the variable names that you want to bind the return values to. And the second option is the form that you're going to get the multiple return values from. This happens regardless of whatever function that you use that returns multiple values. If you're using multiple value bind, you could specify a set of variables that you want to bind to and the function call. And behind the scenes, Common Lisp will just go ahead and split them up and assign them to their appropriate variables in the order that you specified them in this original list. That makes sense for folks?
One thing I'd like to add to that is
Sure, go ahead.
that one of the reasons why you don't need to learn about multiple values right away is that if you don't specify something that expects multiple values, something like multiple value bind or nth value or one of the other like 6 or 7 different tools in the spec that let you access them, it discards the secondary or such values, and you just get back the first one. So for the most part, if all you care about is the first return value, you can pretend like multiple return values don't even exist, and it'll just work. So
that's a very good point. By default, all Common Lisp functions will always return, obviously, the first value. But for in the case of multiple return values, as Elijah rightfully pointed out, you don't have to worry about, if you really need those other multiple return values, you can leverage this guy, multiple value bind. But the discussion of returning multiple values is not an immediate thing that you need to worry about, just because you can always use the first value and then go from there. So Common Lisp has several ways of actually iterating through a hash table. Was there a question? I thought I heard someone who wanted a question. So Common Lisp has multiple ways of actually iterating through a hash table. Let me just add a few, things into my hash table here. Just for example, let me actually reset the hash table and throw that guy away. So I added some nonsense in here. add this guy, and add a couple of more things into our value. So the first way, obviously, like many other things that we've seen with the collection classes, is the map hash function. The map hash function takes a anonymous function or a named function of some sort, has a first argument that iterates through key values. It has to be two values, and the hash table. And when you run this guy, you will actually see it iterate through each of the individual key value pairs and go ahead and apply that function to each key value pair. So it's actually iterating it through it like a loop. Another way is, of course, the loop macro has one of these beautiful things of actually being able to split the hash table. It makes it a little bit cleaner to read, to iterate through the hash table too. And the key is obviously there's this thing called hash keys that internally the loop mini language actually recognizes as that the next argument in after the in is a keyword, is a hash table. So it will do some type checking to make sure that the hash table is there. And then if you want to use the hash value, you have to say using hash value, and it will bind for this given key k. Oops. This given key k, the corresponding value into v, and then it'll just iterate through. So this here in this case will do the same exact thing that I showed above. Loop actually internally uses the third approach that I was going to show you now. This is only for illustration. I don't normally recommend people actually doing it this way unless you're doing like some macro development. It uses a lower level construct called with hash table iterator that allows you to specify a binding, like in this case iter, and a hash table has a hash table that it's going to get an iterator from. And this returns essentially a function that you can then call. In this case, we're calling it through loop, and it returns three values. It returns whether or not an entry exists, what is its current key, and what is its current value. So if you really wanted to look at this, you can certainly run a macro expansion on this guy, which I'll just show for illustration's sakes. And you'll see here, just show this guy off, that this is what it gets generated. It creates essentially a simple anonymous function here called a recursive function called iter that returns those three values. The three values that it's returning is all the way down here. Key, SB impl, key and SB impl value. And then internally it creates essentially an assembly block because it's a tag body, which is an advanced thing that we'll see later on. There's a couple of things about blocks and tag bodies that won't go through too much detail here, but you will see when you do macro expansions. But it's essentially like labeling a block of code so that you can jump to it by using the go statement. So yes, Common Lisp does have go-tos for folks coming from other languages. But again, as I said earlier, I don't recommend you using with hash table iterator. For most things, I personally just use map hash. I don't know what other folks here use. Some folks might be using loop, but I personally use map hash. So that's what I recommend to folks who are iterating through hash tables.
Yeah, this is one of the cases where the iteration constructs in the spec are a little lacking, in my opinion. Loop is verbose and a little ugly for this, and map hash it forces you into functional paradigm, which isn't bad in every case, but it's sometimes a little awkward for what you're doing. I don't know. There are libraries, there are iteration libraries that you can load in that are much cleaner for that kind of thing in some cases,
Yeah, and I think one thing that as we go through this, that I have seen, it seems that people are settling that limitation with loop with like libraries like iterate that I think might be nice for us to demo. It's just that there are so many different ones that that I wasn't sure which would be more appropriate. Iterate seems to be like a lot more folks have just said, okay, iterate looks clean enough, let's just use it. But this is what's already available to you, regardless of which implementation you actually use. Map hash is available, loop is available, and technically with hash table iterator is in the spec. So it should be available, but again, I don't recommend using it. Use approach 1 or approach 2. So these two are what you would almost always use. Or you could always, if you know your key already, you could always just use get hash directly, and you don't have to really, do that.
Yeah, and for cases where this kind of sounds kind of dumb, but for cases where maybe performance is not that much of an issue, if you're writing a quick script or something, or if you're just trying to debug, you're trying to loop over the hash table to do a printout, you can always do Alexandria to convert it to an A list, and then you can just loop over that list. That's a technique that I do pretty often, just because it's a lot shorter code-wise than this.
Absolutely, and I don't know though. I mean, the map hash one looks kind of clean for me. So
right, yeah.
That's the one that I always end up going with, just because it's
map hash actually gets a lot more attention by implementations. Not too long ago, I did a test, and map hash was considerably faster than the loop implementation.
Really? Oh man,
that's actually really good to know. I need to update some code.
I'm going to put this down as fastest by some benchmarks.
At least on SPCL.
I mean, it's the implementation that matters.
Right. Folks who are watching this on YouTube Live, I think, the easiest thing is do some timing if this ends up becoming like obviously a bottleneck for you to see which one is most appropriate for you. But I think there are many ways of essentially going through and leveraging a map and iterating through a map. So it's really both code cleanliness is always number one for me, and preference. If that matches your performance needs, then then great. Otherwise, just pick whatever you're most comfortable with for your own specific use case. But just don't try and unless you're really knowing what you're doing and you feel that this will really help you, I don't recommend using this, because I think internally, again, Loop already uses it, and it really depends on the implementation on how fast you'll end up getting this kind of this code or not. So
yeah, there's also a little bit of a gotcha that might not be super obvious, but the hash table iterator, it's only defined within that dynamic extent. So if you can't, for example, return that iterator and call it afterwards, because it's kind of undefined behavior.
Right. That's another good point.
That's a little bit more advanced usage,
but it's definitely a good point, which is this guy, the iter variable here, which let me just go ahead and expand this to iterator for folks who are watching this. This variable, this function, is only bound within the form. So as soon as you exit this, you will have essentially a nil object, and as Fredo rightfully pointed out, it is undefined behavior. So I will cautiously warn you, bottom line, don't use hash table iterator. I'm just showing this for iterative purposes so that you're available with this. There is some Lisp documentation that mentions it, so it would be wrong and not to mention it as well here.
Ram, a quick question about that. If I had that thing and I had the iterator in a closure, is that a special variable, or would that work properly in a closure?
So the variable is still alive, but the problem is the behavior of the iterator still being live. You can still use it. It's only within the dynamic extent of the with iterator. So as soon as you exit that scope, even if you grabbed a copy of that iterator, it's still undefined behavior to actually use it after that scope ends. That's the gotcha right there. Is that it's not like. Oh, go ahead.
Does that mean that it's probably like a special variable for most implementations if I can't rely on it?
I mean, the variable itself is not a special variable. So the variable itself, it is a lexically scoped thing, but the object that it's bound to is not defined to work outside of that scope. Does that make sense?
Okay, yeah, sure. That's why I was wondering, like, if it was in a closure, because it's,
Yeah,
you know,
it's kind of like if you say you open like a stream to a file, right, and you close it, but you still have the pointer to the actual stream. If you return that stream, you can't really use it out of the context.
So it's like a couple levels down or whatever, basically.
Right. And I think to add on that, like in general, like all the with macros is resource management. Think about it like this: you're blocking the area of code that this resource is available, and outside of that, it releases its resources and it releases whatever it needs to do. It finalizes it. The easiest analogy to other languages is if you ever use C#, it's like the using statement, or in Java, it's like try with using resources. It's the new one that came out with Java 8. So it's the same idea. This is not just specific to the with hash table, but with all with macros. The general pattern is you initialize the resource at the beginning of the with macro, and you at the end of the with macro, it's supposed to release whatever it's leveraging, any files, any database connections, anything that you're leveraging. So this with should be an indicator as to what its behavior really is. I haven't seen. I'll just say it this way: I haven't seen a with macro that does not behave the way I'm explaining it to you. And if it is, I would say that it's a bug.
And a quick amendment, because I realized that I was throwing around dynamic extent. And so that's a terminology like specific to Common Lisp, and to the point where I kind of like use it casually now. But what that means, like whenever you see dynamic extent, I don't think that I can properly explain it, but it generally means if you have a lexical scope, when the binding is established, like when that binding leaves, that's the dynamic extent. Is like you can attribute it to the lexical scope.
Yeah, like it's the same thing as like dynamic bindings, right? It's the same term there, the same use of dynamic. It's when you dynamically bind a special variable like we were talking about before, you now have some context where any references to that special variable refer to that particular dynamic binding, the innermost dynamic binding on the runtime control stack, right? Every time you introduce a dynamic binding, it gets effectively pushed onto some stack, and the moment you exit that let scope, that dynamic binding leaves the stack. Similarly, with dynamic extent allocations, there's some section of the code during the time of which that code is being evaluated, that object is valid, and the moment you leave the evaluation context of that section of the code, you have no idea if that object makes any kind of sense to refer to anymore, and actually a lot of systems like SBCL specifically will treat a dynamic extent declaration as a request that it allocates anything that whatever gets stored in that variable, it should allocate that actually on the runtime stack, right? Just like a local variable in C, if you ever, worked with that, right? And if you like return a pointer to a local variable in C, right, that's all kinds of bad, because that's a pointer directly onto the stack, and that memory is going to be reused for later stuff. Right? And so if you return a pointer to something with dynamic extent, it's the same thing. You have no idea if that memory is being reused for something or whatever, right? It like the moment you leave the dynamic extent where that object is valid, you should, pretend it's no longer a thing at all.
Since we're on the subject of dynamic extent, because it was brought up, would you and this is something that is I'm sure a lot of folks would love to to hear a good explanation of is, would you say that for dynamic variables, like anything that is set with a def parameter or def var, the section of code of that they're located in would be, well, section of memory in the memory layout, that they're located in when they get initialized, would that be the same where any variable that has dynamic const will get allocated? Would it be in the same memory region?
So the value that you're binding, right?
Yes. Mhm.
No, values that you bind to a dynamic variable aren't automatically dynamic extent themselves.
Mhm.
Okay.
You can make them dynamic extent by declaring that binding as dynamic extent. You can do that, but they aren't automatically dynamic extent themselves. If you dynamically bind a variable to some value, the binding is allocated in dynamic extent memory, I guess you could say, but the object that got bound is not.
Right. The symbol is in dynamic extent memory, but
In a
the
sense.
value that you're set effing in this case is not assigned there. It's probably in the local memory region of the
Right.
of where the scope that you're actually leveraging.
Something
So
along those
the
lines.
reason I'm bringing it up is it goes back to what we talked about a couple of weeks ago about dynamic variables and special variables, which is, it really is like, if you're really thinking about it, you're coming from other languages. For me, the closest analogy that I've always bring this up to folks is think of dynamic variables and anything related to the dynamic variables at the process level. Like when an operating system process starts, like an application starts up, there's a region that gets inherited by that process before it gets exec. Those variables are dynamic variables in the operating system sense, and then they're the same thing, because if you change the variable between processes, the previous process is inherited a different value than the current process that has been instantiated. So, I mean, if you think about it as environment variables in your shell, I think you will see some of the interactions that occur when you're using dynamic variables. But I only use them for multi-threaded applications, so I can't.
There is one case where that particular analogy does break down, which is that if you assign to an environment variable that's local to your process, because environment variables actually get copied when your process is created.
Right.
If you assign to a dynamic extent binding, to a dynamic binding on a special or dynamic variable, that actually modifies that binding.
Unless you use a let, right? If you make it special and you make it
well, no. So yes. So the thing is there's a distinction between the binding and the variable, which is important to remember.
right.
A special variable, a variable that gets dynamically bound, right, can have multiple bindings to it, right? And I guess you could say, innermost or most recent one on the current thread is the one that you get when you reference that variable.
Right.
Right. And you can assign to that binding. Right.
Right. So
do you see the distinction I'm making there?
I see the distinction that you're making. Basically, you're saying that there's a scope table that I'm essentially leveraging every time I'm accessing a particular binding that whose value might be different than the outer scope that it inherited from.
Right.
So
like what you're describing is like if dynamically bound variables worked exactly the same way that processes worked, if we're imagining, say, functions are processes in this system, which I think is a fair way of thinking about it, right? Then if I let bind some variable like star a star, right, to be 5, and then I call some function, and that function assigns 6 to star a star, right? And then after that function returns, I print out star a star, right? I would still print 5 because calling the function would have copied the binding into
Right.
the environment of that nested function, right? But
Right.
that's not what happens. It prints 6 because assigning to the dynamic binding reaches up to the most recent place where you let bound that dynamic variable and modifies it there.
Gotcha.
Yeah,
So you have
yeah.
so for folks who are probably getting confused by this discussion, it really to really understand dynamic variables honestly requires a little bit of an introduction to, I think, symbol tables and how
Symbol
scope is
tables
actually
and
defined inside.
stacks.
Yeah.
Let's look, like, really what it is every time you let bind the dynamic variable, right? There's sort of 2 different ways it could be implemented, and I'll talk about one of them. And it doesn't really matter that there are other ways to do this, just that you have some intuition about one way it could be happening, right? One way that you could do it, for example, is there's a symbol table, right, that has a bunch of values associated with all the dynamically bound symbols. And every time you say may def parameter some star a star to be nil at the global scope, right? And then you might fair enough.
I'm just illustrating while you're going. Go ahead.
Yep. Then you might let bind star a star to be like 5, right? And in some body of code. And the thing is, the moment you do that, it takes the one way of doing it is it could take the outer value of star a star, which is nil, save that on the stack, and then assign 5 to star a star just for you. This is one way it could do it. And then when you use star a star in this context, right? It'll look up in the symbol table like it always does, right? But it'll find 5 there. And when you leave that let scope, it'll know to go take the value that was on the stack for that variable and restore it immediately into that special variable. That's one way of looking at it, except the symbol table in this case is local to each thread, right?
Right.
Which is kind of important. But so if you then the other thing is that if you let bind a to be 5, and then inside of that let bind a again to be 6, right? The same thing happens. It goes through. It pushes nil onto the stack, and then it pushes 5 onto the stack, right? And then it pops 5 back into the spot in the symbol table, and then it pops nil back into that spot in the symbol table. So it's this so that way there is this spot that it can always look for the current value, and the old value gets saved. And that way, if you define some function that, say, increments your special variable, right? So define some function inc a that sets increments inc a star, right? And you call that somewhere inside that complicated bit of let nesting you've got going on there. You can sort of see how it does modify the current binding, right? It actually mutates the currently active let binding on that variable. It doesn't copy it into the inc a function, and any modifications would stay local to the inc a function.
Right.
So that's why it's important to like the environment variables analogy is valuable, and it's good to get a handle on when you might want to use dynamic variables, because the use cases are very similar, but at the same time, this is one of the big differences, right? Because if we were talking about this in the form of functions are processes and dynamic variables are environment variables, the last print there would print 5.
Right. The last print there should print 5 instead of 6.
Yeah.
Right. Right.
So, I mean, that's the distinction, I guess.
We can go. I think.
Yeah, like we could probably dedicate a whole session of this just to talking about the uses and the complexities of dynamic variables.
I think that given the number of times it's been brought up, it might be important for us to bring this into light, just so that more folks understand how it kind
Perhaps.
of works. I'm just going to, I don't know, I'm going to make a note of it just to see how we can leverage it at some point in time. Okay. So that's our basic discussion of collections inside Common Lisp. To summarize from last talk and this talk, just to give you a summary of Chapter 11. We've visited vectors in Common Lisp. We've visited hash tables in Common Lisp. We visited actually technically lists in Common Lisp already in some way, shape, or form. Although Chapter 12 is going to give us more detail about how that's available, and I'm going to say up front that this is not the end of the data structures that are available. There are plenty of third-party libraries that implement a lot more than what we've mentioned here. We've just provided what is in the current standard, and that was actually reviewed inside Practical Common Lisp. And I will briefly also mention before we move to Lisp processing that both list and vector, as I think I've mentioned before in past talks, are actually subclasses of a much larger thing talk about, which is sequence. And if you wanted to, you can actually subclass that guy and leverage it. Although there's an entire thing about sequences that I don't want to mention here that you'll end up hitting if you try to do that yourself.
That road is fraught with implementation defined behavior.
Yes,
man.
That road is very much fraught with implementation defined behavior. So, as I mentioned, right, Lisp stands for Lisp processing originally. That's what it stood for, the Lisp processing language. And it was built on top of the Lisp data structure, which uses, which was a generic data structure of different types. It was actually built on a more primitive thing called a consel. Consel basically was named after the function that was created, but also at the same time it was it was related to the architecture of the first machine that Lisp was built on, the IBM 704. When you first create a consel, and let me just go ahead and print this guy so I can actually see this when I compile this, you will end up getting something called a dotted pair. Now, the reason why this is a dotted pair is it's an object that that has two distinct pointers to two different memory locations, a car and a cater. Car stands for content of address register. All right, and this is a very historical name for, and again, it comes from the 704 architecture that Lisp was created, and Kitter represents contents of decrement, part of register, and these two just sort of stuck on as Lisp sort of grew, and the libraries are available, and it just all later Lisps ended up leveraging them and just kept them as is. The functions sort of persisted, but for people who use lists, as you can see here in this example, when we create our first list, you'll notice that lists are actually just don't show up as dotted pairs, and that's because internally they Common Lisp and other Lisps as such who uses consels, they sort of hide that they're consels, but you could just call car on a list and get the first element of the list, and Kitter on it to get the rest of it, and that's really a pointer to the rest of the list. And you see that becomes a sublist. Now, Common Lisp has modernized since these were introduced, and they do have the sort of what I would say the modern normal equivalents that most people are familiar with, which is first and rest. So you can, and I almost always end up using these nowadays, just because a lot of folks, if I use car and Kitter, they start to get irritated with me. So I recommend folks who are starting off with Common Lisp, if car and Kitter sort of like throw you off a little bit, you could always also use first and rest to actually do the same thing. Does anyone have anything to add regarding that? Cool.
For
All
just lists? No, not really. That's pretty much it.
right. All right.
I tend to only use car and CDR when I'm working explicitly with dotted cons cells
Okay.
or cons pairs. When I'm working with lists, I always use first and rest just to make my intent clear to the reader.
Excellent.
Yep.
So we're all in agreement. If you're using con cells directly, car and kiter does work, and it actually is nice to use because it expresses, like Michael rightfully pointed out, intent of the code, because you know what the type is almost just by the function call that you're using. So the chapter 12 introduces some introduction to functional programming, which I think, given nowadays, I don't really have to give much of an introduction to. But just to reiterate, functional programming is based on this. It's a paradigm that functions are essentially mathematical in nature. They map values from one set to another set. So what you normally see in math notation, goes from X to Y, where X is a set of values and Y is a set of values. The notion of functional programming follow the same idea for functions, and that is functions do not mutate any sort of state. Lisp was one of the first languages that had this kind of feature, more like functions as a first-class citizen, and it encouraged that style, especially on lists, on the list manipulation functions, and it did it for a reason. But before we get that, because I'm getting a little bit of ahead of myself, just to show you that these list manipulation functions do not, actually modify the lists that they're provided. I've created a parameter here called a list, and if I call reverse on the a list here, you'll see that if I print the a list out, its actual values have not changed. It was not actually properly reversed. It wasn't stored. It wasn't an in-memory substitution in sort in the opposite direction. There are things called destructive operations in Common Lisp, and there are different types of destructive operations, but I will show you that these destructive operations obviously do show that Common Lisp, even though the Lisp manipulation functions are written in a functional style, and you can write in a functional style in Common Lisp, a good portion of the library is written in a very destructive style. And to show that, if you use this function called nReverse here, and to reverse the list, and you don't set it like I did right now, if you tried to print the list out, you might be thinking, oh, it didn't, it didn't change the list, or it didn't in-memory replace of the list. No, what it actually did is it sorted it out and popped things off the list, and now you only have the last element of the list that you've returned as being part of the list structure itself. This sort of is is a surprise to folks. So when you want to do something like an in-memory replace, and this is what it ended up compiling down to, you must do what essentially is a set F on the variable that you're trying to call, and then run the destructive operation. Otherwise, you're almost guaranteed to lose that. I will say that I've done this myself, so it's a common thing to happen when you're learning the differences between destructive operations and the functional operation equivalents. The reason why a lot of Lisp functions are written very functionally, as it's mentioned right here and it's mentioned in the book, is the fact that there's a lot of performance is related to allocating deallocation of con cells, or consing, so to speak. And if you're passing in for certain list operations just a list, and you just want to minimize the amount of constants that you're creating, it's easier to just pass in a list pointer, and then list behind the scenes, since they're all const cells, will know how to essentially share the structure of the list data structures that are passed in as arguments. So like in this case here, when you appended two, let's say that I created, just create a append list here that takes the return value of this guy. And if we look at append list here, we see 1, 2, 3, 4. You might be thinking, oh, okay, because this was written functionally, that means there were 4 consts that were created. That is, each element ended up getting a const construction and a copy that was created. But that's actually not true. What ended up happening is the first list, 1 and 2, were actually recreated and copied. And what happens is 2 dots tail, which is, I guess I could just say 2 dot there. It ends up becoming the car of the second list behind the scenes. And that means you've just saved yourself 2 additional cells being reconstructed for memory and throwing out 4. So you only your total cost of allocation is 2, not 4 anymore. And this happens in a lot of the list library functions. It's one of the nice things about the way Lisp is generated. But it does create for certain interesting and unexpected behavior for folks who are starting out. And this I got straight out of the book. Let's say that you run, you have these 3 functions. So 2 lists. Our third list ends up becoming the appending of the first and the second list. So let's say that we go and decide, you know what, I'm going to change the first list value to 0. All right. Wait a second. Oops. 1 second. It's supposed to be a comment. Let's say that I created the first value to be 0. Right. If you evaluate list 2 here, it'll give you what we expected, all right? Because we changed it, we explicitly said, hey, Lisp, go ahead and change the first value to be 0. But because list 3, actually shares list 2 structure by changing the first of list 2, you've essentially changed list 3 behind the scenes. So you have to be a little careful when you're leveraging these things, because again, because of the shared structure, it does make Lisp manipulation very efficient, very easy, very convenient. But it also has these gotchas that if you're not too careful, and if you didn't design your code to be written in somewhat of a functional style, that you end up changing something that you didn't want to change, and that looks like undefined behavior, but it's actually a design decision that was written behind Common Lisp. Are there questions about this? Because this is something that I was confused on when I was first starting off on this. Cool.
Yeah, basically don't ever modify a list that you didn't create and know couldn't possibly share structure with some other list. If you get a list from somewhere else, copy it. That's the rule. If you're going to be modifying the list, if you get the list from somewhere else, copy it.
Yes, always, if you're going to get something from someone else, copy and do the operation is probably a safer bet than anything else. Don't assume that there's some structure that's written functionally.
And don't create a list with quote. That's a list literal.
Yeah.
Oh yeah, that's also a bit of an issue, because this is actually a really fun little demo you can do. Here's fun. Defun just some foo, right? Takes no args and returns a quoted list, right? No, containing something. Yeah. Right. Now, call foo, right? Now, store the return value of foo in some variable, or just set f first of foo, first of the call to foo, right? You want to call foo and get
Oh
its
yeah, right.
list.
That's right.
And set f that to be like 5, right? Now call foo again.
Wow.
Yeah. Because the thing is that list, right? When you
Right.
quote it like that, it actually becomes part of the code, right? And so when you call foo, it's always returning the same actual pointer.
Right.
It's not creating a new list. Quote creates the list during parsing and saves it in the structure of the code. So never modify a list literal.
And before anyone gets ideas of like trying to use this,
Oh,
this
yeah,
is technically undefined behavior.
Yeah,
Like-
yeah. This is literally like
Yeah,
that.
don't
that
try to
list,
use
like,
this as an optimization or just
Yeah.
like be clever or whatever. This is undefined behavior that will break on some
Yeah.
other implementation or on some other compiler settings.
Yeah, because like it might not even properly allocate that list the way you expect it would, because it knows that that list isn't it's allowed to assume you're never going to modify it, and so it could use some specialized representation of a list that's not really a list internally but stores the values you want, and then modifying it could cause all kinds of chaos, right?
Bottom line, don't modify lists. If you're gonna use lists, like
Yeah.
I learned my lesson when I was playing around with this, and I almost
Yeah.
always write my code just with respect to lists, almost
Yeah.
guaranteed to be functional. It's in
Yeah.
nature with respect to Common Lisp and the heterogeneous list structure that they provide. It's just
The
not
other-
worth your time
Yeah.
trying to do this kind of crazy things.
The other side of it is that actually it's not just quoted not just quoted lists. Like pretty much firstly, anything that you create using quote, never modify it because it's part of the code. And also anything like any arrays that you create using the array literal syntax, right? Like hash parens to create a vector, never modify that vector. That vector is a literal vector.
Pretty
It
much
could-
anything with the sharp sign, sharp dot for the reader
Yes.
macro.
Yeah. Anytime you're creating something using the sharp syntax, right? That's considered an object part of the code. It's not something that's being created every time that code gets run. It could have been pre-created and cached and optimized away in weird stuff. So never modify those things.
There are plenty of manipulation functions that are at your disposal. I just wanted to briefly mention two things that I thought were interesting in this chapter, but obviously there's a lot of chapter 12 goes through a lot of functions that I encourage you guys to actually go through and actually play around with. Things like delete if, delete duplicates, which are extensions of remove, and substitute. We've gone through a couple of these in the past, and it'll be mostly review if you've done at least the collections library. But there's this notion about the differences between what they call for side effect functions and recycling functions that that Peter brought up, that I thought was a nice way of at least explaining what is some of these concepts. And we've already seen an example of a for side effect function. Sorry about that. And that is n reverse. I mean, it's a recycling function. Recycling function means essentially in Common Lisp non-consing. It's just going to leverage whatever block of memory that you've essentially passed in as a parameter to do what it's going to do. And this is why you saw the result that you did when we did a destructive operation here, when we tried to print the n reverse of the list that we created here in this example. But for side effect functions are essentially behind the scenes. They call this guy. Set F, for the most part, is your generic assignment operator for anything in Common Lisp. I haven't seen an additional assignment operator that doesn't essentially boil down to a set F. Even I think do people still use setq? I mean, I don't know. I think
There are cases where setq actually recompiles to setf, amusingly enough. So there's no reason to ever use setq. It's completely deprecated by setf.
So if you guys see setq in code, just be aware that setq essentially is a setf for the most part. But setq is was a set operation that was in the Common Lisp library. But both of these essentially modifies the particular argument, the variable that you specify with whatever you pass in has a secondary parameter. And because of this, functions that internally leverages this operation are called for side effect functions. An example of functions that really do this kind of pattern, which are for side effects, is actually something that we've seen when we talked about vectors, which is vector push and vector pop. But I will say that those of you who are probably saying, oh my God, there's no vectors that we can't do, functional programming with. This is just ridiculous. Oh man, I should just go ahead and use, something like Haskell. I'm going to say right now that it wasn't designed. Common Lisp's vectors, libraries, and collections, high efficient, was designed more for efficiency, from what I've read in other literature, than trying to encourage more people to leverage the FP paradigm. And in almost all cases, if you were going to go and write functional program code in Common Lisp, you'd leverage lists in some way, shape, or form. And they did a lot of work to make lists as efficient as possible inside the language. But again, the chapter does go and mention those two things, and I thought it would be interesting to at least discuss the differences between them. There's really not too much in this in terms of other like interesting like functions, but I will point out that because you have this car kitter sort of console structure that's built in functions, you can actually leverage the console to also creating things like trees. I'm just showing this as an example. Don't try and do this, but this internally is essentially like a tree in Common Lisp, and you can call things like copy tree, and it will take this object and create a tree, copy it, and it knows how to deal with that internal shared structure and return the appropriate tree object. So concells itself really is something that you could play around and create a lot of different types of shared structures. And it's a very fundamental thing in all Lisps that you should really sort of take some time to kind of like play around with and understand. Is there anything else I'm missing by the chance, senior folks that are on regarding concells? All right. So that's oh yeah. So the other last part that I was going to mention is because we were talking about functional programming here and just talking about functional programming in Common Lisp, is map that we saw before. We did map car before when we were talking about lists originally. Just to review, you have let's say that just trying to double elements of a list. You pass in a list, and it will go ahead and return another list. So in the case of, say, what I did earlier, if we just take a list and pass it in, if we actually return a list, notice that a list isn't modified. Map is one of those additional functions that does not modify the list. You also have reduce, as we have seen before, that will reduce everything that's inside a list and return it. But again, it doesn't modify the list either. There's a whole slew of map functions that honestly I haven't used them all. I'm going to be upfront. I almost always end up leveraging mapcar or map list, but that's about it. I don't know if others on the call have leveraged some of the other ones that were mentioned in this chapter, but the reason I'm not bringing up those, and I want you guys to really experiment with the map library is you might find it useful in your particular use cases. I'm just mentioning the ones that I actually am familiar with. Elijah, do you have anything to add regarding map or reduce?
Not really. I mean, there are an awful lot of iterations. Just like,
Yes.
yeah,
That's what I figured. All right.
I mean, there are an awful lot of iteration macros and functions and such in Common Lisp, and there are an awful lot of just like, honestly, every time I go back through and look at the sequences API, I realize I've forgotten at least half a dozen of the different iteration utilities for
Right.
operating on vectors, like find, search, what is it? What's the one that lets you find where two sequences differ? Because there's a function for that. There's a function where you give it two sequences and it'll tell you the index where they differ. And I can never remember what the name of it is, but I know it's there. This is like
yeah, and there's a lot of like folks who because if you're leveraging things like, and you're creating higher order functions, and you need to do like things like dumb like you want to do reverse iteration. I've shown you first and rest here. Well, there's also last and but last.
oh yeah, don't use those. They have linear time lookup cost.
Right. These are
yes.
But it's very useful because in one particular case, because if you look at how you write compose,
True.
which needs right to left application, you'd want to be able to, and those who aren't aware, I'm not going to sit down and
To be honest, though, I'd probably reverse the list first and then iterate through it.
Okay.
Because the trouble is that if you item by item go through a list in reverse order, that's n squared complexity. Whereas if you reverse it once and then go through in order, that's linear.
That's true. That's a very good point.
So
But
I almost never use last and but last. Occasionally, they are precisely the thing you need. But and this is true of like
for
a dozen different.
It's extremely useful for one thing I know of, which is function composition. And in that case, you're assigning it anyway, so you're paying that linear cost up front before you pass it into a reduction to do the function application. So if you use like compose here that I showed you, and let's say, and I'm showing you guys a quick example here. Alexandria has the compose function already built in. If you wanted to say take a value and just increment it after doubling it, and let's say that we call that guy double then increment, double then inc, for lack of a better name. Then I could just call this guy, and behind the scenes what it did is it literally just took this list, reversed it behind the scenes, and then applied it before it created the final lambda function that you see before you. You can call this directly. Oh, sorry, I have to say double then inc on your list, and it will go ahead and what? Wait a second, did I change that? Wait, I messed that up. Hold on. Oh, I missed.
You don't need a hash quote on that one.
Oh,
it's a variable, not a function.
Ah, yeah.
Yeah, so, no, you get used to that eventually. After a little while, it starts being really obvious, but
I always, I'm always forgetting that. Yeah. So you could just call the function directly, and it'll go and apply it. But what it does internally is compose itself. The Alexandria compose guy that I just leveraged here. It actually reverses this list and then creates the Lambda function to apply this application. And if you look at the actually, I think I can I don't know if it implemented this as a macro or not, but let me see. Oops, it didn't implement as a macro. I was going to show you is that sorry. Actually, you know what? Give me just 1 second. I will show this to you guys because this is a very particularly interesting thing, which is give me 1 second. Which is okay. 1 minute. This guy go into here. I'll go into. So let me share this to you guys because I think you get a kick out of this. Screen share, application window, this guy. It was in. This is actually a book called On Lisp that has some really nice functions. Let me just do something here. Where was it? It was in. I think it was in functions. What was it? Hold on.
Oh yeah, on Lisp is a good one.
This is one of I almost always keep this with me, but unfortunately, it is just not doing what I asked it to.
Define compose. It's right there.
Here we go. That's what I was looking for. This is essentially what Alexandria Compose does behind the scenes. All it does is it takes a list of functions, which is a rest parameter, checks to see if it's empty. If it's not empty, it'll just pass it. If it's empty, it'll pass the identity almost always. If it's not, this is the only situation where I've seen last and but last being useful, at least, which is you take the last argument because you need to apply it first anyway, and the rest of the arguments that you want to leverage. And reduction actually has a keyword parameter, the ability to do reverse iteration, so you could go from behind. So you could do from end true and apply fun call to each of the functions in this list in reverse order. But you need only the rest of the list. As Elijah rightfully pointed out, you could simply change the ordering if you did before creating the composition. But that's in this case not necessary because the runtime cost is still linear in both cases. Here you're just assigning it, but I only mention it because it is one definite use of last and but last. There are other cases, I just haven't found them. Let's see here. You can build some very nice functional utilities using Common Lisp. Really, to summarize, we've only discussed a few of them here, but that's all I have for today. Are there questions? Ooh, there's a bunch of comments. Oh. Questions, comments, complaints. Oh man, you didn't go through a lot of stuff. Oh, all right. Next time, I guess if there aren't any questions, we'll just end this early a bit today. Next time we will be discussing Chapter 13, which is other uses for con cells. And if we can get some time, we'll talk about the awesome file library that's in path name library that's available in Common Lisp, because I'll be honest.
No.
That's a funny.
I've been dealing with that for the last like 2 weeks, 3 weeks, 4 weeks. I lost count at this point.
I know, Will. I know. That's why I brought it up.
Yeah.
I'm going to, remind everyone again. Those of you that just, just final announcements, which is really keep on the lookout for more information about the Lisp Game Jam coming up in April. I'm going to keep mentioning it here every week, just so that we start seeing some awesome folks coming into writing some games on either Clojure, Lisp, Scheme, Racket, your choice of Lisp. Just submit your submissions. We have the organizer with us. If there's anything do you want to add anything regarding the Game Jam right now, Michael?
No, a couple people asked if they could work in teams, and yeah, you could work in teams. I just want to throw that out there. I think Wilfredo actually was looking for a teammate.
Yep. Right now, I'm planning on working with Ethan Morgan off of the Discord, but I mean, more the merrier. So if you're interested in participating, whether you're experienced or 100% new, I don't really care. I think it's a good learning experience for sure.
Yeah, that's all this is it's for learning. I mean, even if you're a newbie and you never did this before, please try to participate and have some fun.
Yeah, absolutely.
Don't be afraid of experimenting. I mean, we're all here to learn. At some point, we all started out as new. Do not worry about making mistakes, because the entire point of these kinds of game jams is to experiment, go a little bit out of your comfort zone, and try some new things while you're developing, and to meet some really cool people. So next time, again, chapter 13 and 14 on Practical Common Lisp. Until then, thanks all for joining us, and I hope to see you guys next time.
Thank you.
Thank you.
Thank you.
Bye then.
Thanks. Arigato.